Okay, so part 2. This is part 2. If you didn't see part 1, I don't really know what to tell you. Go back and watch that. There's probably a link somewhere. But again, I'm not that great at YouTube. I'm not even good at cameras. Look at that. Okay. So here's the problem. I have my moon right here, my model of the moon, and then I change it for a bigger Lego piece. So here's my Lego piece. It's going to start. Oh, that's R. I'm sorry. This is 2R. And that's 3R. Okay. So it's going to start up here at b equals 0. And then it's going to fall down to there. And the question is, how fast is it going? So in the previous example, you like my little space object on a stick? In my previous example, what I did was to use the momentum principle. And since I have a non-constant force, I just found the average force. I'm like, what the heck? I'm going to do the average force. And I used the average force and this change in y to find the final speed. And that's what I did. Okay. And then I got this, I put it up here, 1,009 meters per second. So now what I want to do is do it again, but take into account a better way to deal with non-constant forces. Again, use the momentum principle. So here's what I'm going to do. There's my object. I can calculate the gravitational force on it. Let's just call it F. There's only one force acting on it. Okay. And so if I know the vector R, the location of that, let's call this the vector R, then I can find F. F is negative g, mass of the moon, mass of the object, over the magnitude of r squared times r hat. So r hat is a unit vector that points away from, in the direction of r. And that's important because if you don't have that, then you don't have a vector for the force. And I need a vector for the force for the second way I'm going to do this. You could do this, and I'll do it both ways, in fact, in the video, which I'm going to have attached to here. Okay, so once I calculate the force, then how do I deal with the momentum principle, which says F net, which is on one force, is the change in momentum over the change in time. Well, from that, I can solve for the change in momentum. And in fact, if I know the momentum, I can find the new momentum if I have a short time interval. Well, how long does it take to fall from here to there? We don't know. We don't care, right? Because I'm just going to break it into a bunch of time steps until I get down to there. And that's the goal of the numerical calculation. So I'm going to do the following. Calculate R, because that's going to change. That's my position. I'm going to calculate the gravitational force. And then I'm going to update the momentum. So I'm going to say the new momentum is the old momentum plus F times delta t. This equation is this. It's the same. That is the momentum principle. Okay. And then I'm going to use that to update the new R. Actually, so I don't need this. I'm going to update. So I'm going to say R2 is R1 plus P2 over M delta t. So P2 over M is the velocity at the end of that time interval, and multiplying the velocity times delta t gives me the change in position, so I can use that to find the new position. So I need to know the starting momentum, I do, at 0. I need to know the starting position, I do. And then I can do this. Oh, I need to update time, t2 equals t1 plus delta t. And then just keep doing this until R2 gets to my new location, and then I know my velocity. Okay. So this is a numerical calculation to take a problem and break it into small time steps. How small of a time step? Who knows? I'm just going to pick something. I'm going to start probably with a second, but I'm going to do that in the code, which I'm attaching here. Okay. Now, I'm actually going to do 2 problems. The first one is this going down here. Where's my Lego piece? The second one is, what if I want to go 2R over here? So in this case, I'm not going to let it fall down. Oh, actually, I can't do that. I'll save that for later, because I wanted to see if it goes like this. I'll save this for a final video, and I'll do it 2 different ways. Because now I'd have to start with it with some initial velocity, so it's moving this way, and then I could find the velocity down here. And this momentum principle works. So I'm going to do this actually in 1 dimension just to make it easier. I'm going to make it as simple as possible in 1 dimension, and I'll do that in the code here. Okay, so this is actually the code from my previous example where I calculated the average force and use the momentum principle. So I'm not going to get rid of that because, I mean, what the heck? Okay, so but I am going to, because I want the mass of the moon, I want the mass of the other thing. So let's just start with what we're going to do. We already have our initial conditions. I do need to put in the initial momentum and then the initial position. So I'm just going to say r, and this is going to be in one dimension. Okay, it's not going to be a vector. I will later do a vector version. So r is going to equal 3 times r. That's where it starts. The momentum is going to equal 0. Okay, and t is 0. And dt is 1. I'm just going to pick 1 second time interval, and let's find out if that works or not. Okay, so now I'm going to say while r is greater than 2 times r. So I'm going to keep doing all these calculations until the position gets to 2 times the radius of the moon. That's what I wanted to do. So step number 1 is calculate the force. F equals negative g times mass of the moon times mass divided by r squared. Now, in my previous thing, I said, oh, you have to have a unit vector, blah, 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 but you don't because I'm doing this in one dimension, okay? So I do need the negative because I need the gravitational force pulling it down towards the center of the moon. So that's my force. Next, I'm going to calculate the momentum. P equals P plus F times dt. Okay, so here is something that you may think as weird, and that's there's no subscripts. And you would think P cancels, but it doesn't, because the equal sign in line 25 is not an algebraic equal sign. This is a make equal to sign. This says take the momentum P, add F times delta T, and then set that as the new momentum. Okay, so it looks weird, but it's cool. Okay, now I need to update the position. R equals R plus P times dt divided by m. Just like I said before, I need to update the time. I don't actually have to. T equals T plus dt, and that's it. And then let's say print the final time, just for fun. Let's print the final velocity, and that's going to be P divided by m. Remember, we're always dealing with momentum here, so I need to divide by the mass, and that's going to be meters per second. Let's print the final position. No, that's fine. I think that should be good. What's the chance this runs? I have no idea. Let's save it though, and I will link this code below, and I'm going to run it. Okay, so I get negative 969. I think it's good, right? I think it's good because that's pretty close to the one I got before. It's a little bit slower, and the negative just means go in the negative x direction. My time interval was probably too big, too small, because I had 4,000 calculations, because if I did 4,000 seconds. Let's think, should it be greater than or less than what I calculated before? I think it should be less than, because you are going to deal with a greater force as it gets closer, but it'll be moving faster, so it won't spend as much time with that force. That average force is not really the equivalent average, right? That's just the literal average. Let's just check one thing. What if I make my time interval 10? Let's see what happens to my final velocity. Okay, it didn't really change, right? It didn't really change. That tells me that 1 second was plenty big enough. 10 seconds is plenty big enough. If I change that to 100, I'll probably still get a pretty good answer. But you'll notice how easy it is to change this stuff. See? It's still pretty good. I'm kind of impressed, actually. Okay, so that means I have 2 velocities so far. Here's V1. That's using the average. And here's my new one using the numerical calculation for the momentum principle. So I'm going to do again another video. Click down below or something like that, and then we're going to just keep doing these things forever. It's going to be super great.